Here we're going to discuss one of the two most common ways of doing energy balance on a chemical reactor. In this one, we explicitly use heat of reaction in energy balance, and we do this by picking as our reference states reactants and products at 25 degrees and 1 atmosphere. And a way we can visualize doing the calculation is that we start out with reactants at some inlet temperature, and there could be several reactant streams at different inlet temperatures, but the concept is the same. And we're going to think about lowering the temperature to our reference temperature, called T reference, which in this case is 25 degrees C. So we have reactants at 25 degrees C. We then carry out reaction. So this is the term where the heat reaction occurs, and we use heat reaction at standard conditions, and that's what that O means there. So we end up with products. Well, they're still at 25 degrees C. We then take and raise the temperature of the products and one reactants also, and any inerts that are in there. We raise them to the outlet temperature. And so essentially what we're doing is we're carrying out calculation-wise 3 steps, and we add up the enthalpy change for these 3 steps, and that's equal to the other term in the energy balance. And this term, heat reaction, and this term is going to be a sum of the flow rates, molar flow rates, and the heat capacities, integrating over temperature from 25 to the outlet temperature. And likewise, this is a sum. In this case, we would integrate from the inlet temperature to 25 reactants, and of course any inerts that are also in the feed. So let's look at the equation that essentially does this calculation that we've visually shown here. So here's the equation. Let's go through the terms. This is, and the dot means per time, so this is work per time, so kilojoules per second, and this is shaft work. And this term is the heat added, again per time, so heat added per second, shaft work per second. For most chemical reactors, the change in kinetic energy, so this is kinetic energy, this is potential energy, those terms aren't going to be important. And so for here, this case, we're going to look at them as 0. Over on the left side, the extent of reaction, and there's multiple ways that this is defined in the literature, so I'm just going to show one way. So we have some reactant, again a rate, the flow rate out, flow rate in, divided by its stoichiometric coefficient, where in this case we're going to have the stoichiometric coefficient of units of moles per second, so that the extent of reaction is dimensionless. Other textbooks will define this extent of reaction having units of moles or moles per second. The heat reaction term is the standard way that we calculate this. Sum of stoichiometric coefficients times heats of formation, standard conditions, each component, and then again to make it per time. So this is the values we look up from tables at 25 degrees C. So to make clear, this is a molar flow rate, as is this term here, one flow rate in, the other flow rate out for various species. And this term is enthalpy per mole for each species. In this case, it's integral from our reference temperature. Here we're using 25 degrees C to the outlet temperature. Heat capacity of each component dt, where the heat capacity typical form would be a constant, a second constant times temperature, a third constant temperature squared, a fourth constant temperature cubed. But there are other forms that are also used for heat capacity. And likewise, the enthalpy coming in is, in this case, evaluated from reference temperature to inlet temperature, heat capacity dt. So notice I wrote it the opposite from here, but we have a minus sign here, so it's the exact same calculation that I showed above. So with this equation, we could calculate the heat added, for example, if we know the outlet temperature, or we could calculate the outlet temperature, say, if we know the heat added, and of course in both cases we need extent of reaction. Or if we had the outlet temperature and heat added, we would be able to determine the extent of reaction for a chemical reactor.